Hello, good morning everybody, and welcome to the next lecture in computer vision. We will again look at the semantic segmentation for the last time before we then move on to object recognition and localization then in next week. So, however, before we go to the new topic, which today then will be convolutional neural networks for semantic segmentation, we just want to have a quick look of the problem of actually determining how good the segmentation was. So in last week, you segmented some images using features and support vector machines. So you assign a class label to each pixel. And now what happens if your prediction of the classes does not quite overlap with the labels? So how would you measure that, how good your prediction was? So here would be an example where we have one area that was labeled like this. We have then the area that was predicted, which has the same shape but a slightly different position. So when we can do this on semantic segmentation, we can actually compare the pixels. And so this is a bit easier than to do than next time when we look at object detection, where all of this will be treated as an object. So you have probably seen this slide before in one or the other classes, which gives you the definition of some metrics that are used to access the result. So maybe at the bottom end of those metrics are the four values here: true positive, false positive, false negatives, and true negatives, meaning that if you say it was one class and it actually is that class, then it was a true positive. If you say it was something but it wasn't, it was a false positive, and same is the negative. If you missed one of the positives and assume it's a negative, false negative, and if you found it correctly, then you got a true negative here. So often those values are not used directly as the raw values, but you derive some additional metrics from them. For example, accuracy. Accuracy is just all the objects, or in our case, all the pixels that you predicted correctly. So the true positive and negatives over all of them. However, we will see what is often the case is that you have more from one class than from another, and then accuracy might not be the best metric to use. Other metrics are like precision or recall, which, for example, do not include some of the negative values here. So now, if you want to look at those for our segmentation problem, again, that was the prediction, that was the labels. So what would be the scores of that result? Well, fortunately, we cannot do it so interactively here. So here are the results. So you could calculate the true positive, which are those 4 pixels here that you predicted correctly. Then here are some that you predicted were positive, but they were actually not. So these are 5 false positives and also 5 false negatives here. And then all the rest here, they are negative, and you predict negative. So that would be true negatives, of which you have a lot. And using the formulas from the last slide, you can then calculate the metrics here. So what we see here is exactly the problem that we have a lot more examples of the here, like the background class, the negatives. So we have quite a high accuracy, but the other values are much lower, like precision and recall, mainly because they do not involve the score of the true negative. So often we will see that in semantic segmentation we use precision or recall, or the F1 score, which actually takes both precision and recall to F. Also often used score, then especially also then in object detection, is intersection over union, which is a bit smaller here. It can be calculated from the formula before, but intersection over union is quite clear here. The intersection are those 4 values and the union are all of that. So it's 4 divided by all of that. Okay, so now let's continue with the semantic segmentation. What have we looked at so far? At the beginning, we looked at segmentation only. What is segmentation? It's unsupervised. We try to find regions in images with similar properties, and one approach for that was clustering, for example, with k-means or then with a mean shift to find those. Then last week we looked at supervised learning for semantic segmentation. So this would be the approach to calculate features and then use some classification algorithms on those features. We calculate features usually not just from the pixel value, but from some neighborhood from the pixel value, because in our application we wanted to detect the textures, and a texture is kind of by definition needs the neighborhood to have some specific meaning there. From 1 pixel you cannot determine if it was checkered or not checkered. So the features are usually calculated from a neighborhood, and then we use a classification approach for that. That could be, for example, a support vector machine, but also other classes like a binary figures. We've looked at different features, so there were some rather, I would say, low-level features which are good for texture segmentation, like local binary patterns or those gray-level co-occurrence matrices. We also looked at some features that can be used for textures, but also for a bit higher level than object recognition or higher scene recognition, like histogram of gradients or SIFT features, or some filters in between and combination of those filters. This was the text on where we clustered the filter responses to give a description of the local neighborhood of a pixel. Okay, so far so good. That actually works quite well, but to really make a system out of that, it's a lot of work, because there are many features available that you could try. Not all of them work the same in all environments or for all applications. So you have to find out what features work, and maybe also these features have some optimal parameters, some different parameters that you want to try out. So it might be a lot of time to find the features, and then you have to train the classifier, and training classifiers on large amount of data that you typically have in images or image pixels can take a long time. So why don't we learn the features too, instead of trying to guess the feature and then do the classification? And this is what we're now trying to do, and we can do this with fully convolutional neural networks. So I think you already have seen the approach that we can actually learn the features and use the features then for the classification in the first part of the lectures, where you recognized or classified images. Your project for the homework 1, for example, was to classify numbers, and so the network actually finds the features and then uses the later layers of the network to classify. So when you look back at the neural networks that you used for that, what did those neural networks consist of? What are like the building blocks of those neural networks? And maybe what happened to the image size when it travels through the network? Any ideas? Filters, yes. So your building blocks was filters. These were convolutional layers. Exactly. This is one part of the convolutional neural network. Are there only convolutional layers in such a network, or are there also other layers in the network? And what happens to the image when you use those convolutional layers on the image? Okay, so additionally, when you had you have pooling layers and you have some probably fully connected layers. Resolution reduction, exactly. So the images get smaller over the time. So why do they get smaller? Let's look at those building blocks. So in those networks, you have the convolutional layers. So they act like filters. You learn the kernels of those filters, and actually those filters get applied then to the image and go over the image like normal filters do. And we learn the filter kernels. So you could have filters of different sizes. Usually in more modern network, I would say you have rather smaller sizes of the filters, but larger networks like VGG or ResNet usually use 3x3 filters. Inception uses a different variety of filters and then concatenates the result together. You also have different strides. Now, what was a stride? Stride is that you don't move the filter to the next pixel, but you might skip some pixels. And for example, with a stride of 2, you will skip 1 pixel and then process the next one. So with a stride, it means you will have less results because you skipped some pixels. So the images would get smaller by different strides. By just a convolution, they do not necessarily get smaller. Depends a bit what you do on the border. If you use valid or same to see if the kernel fits in the image, or if you extend the image and fill it with those zeros to get the same size result. Then you have pooling layers. You can use max or average pooling. So we will see that in a repetition, that you look at the 2 by 2 or a larger neighborhood and then just keep the max or average value. Also here you have different sizes and strides possible, and again you will make the image smaller. And usually at the end then you have fully connected layers which are used for the classification. But at that point the image is quite reduced and you would actually get something like features before you go to the fully connected layers, and so you have less data or less pixels, but maybe then more channels in those as input of the fully connected layers. Okay, so these were like normal or convolutional neural networks that we have seen so far. So what is the difference to fully convolutional neural network? Well, fully convolutional neural networks, as the name implies, cannot have any fully connected layers. So all the layers must be convolutional. Why? Because you want as output an image map, and each pixel position of the output will be a vector with the probability of the classes there. So what you have to do is then you convert your fully connected layers that you had in networks that you use for image classification into convolutional layers. It can be 1 by 1 convolutional layers, and then you will have a value for each pixels. So the last layer usually as a result will then have a depth that corresponding to the number of channels. Because you want to make a prediction, for example, for 10 channels for every image, so you get a vector of 10 probabilities with the value of the probability of that pixel for each one of those classes. Since the network is then fully convolutional, there's the advantage that it can work on any size of image, because it will also always result then in a convolutional response, probably of the same size than your input image. Okay, so here is an illustration of that idea. You have input image of some height and width and maybe 3 channels. You have some convolutional layers here. At the end, you have those scores. So you have again height times width and number of channels. And then, for example, if you want a class, you will have the one with the maximum probability here. So if you do that, you will actually get a prediction for all the pixels by running the image once through the network. That's quite nice, right? Well, problem is a bit, for example, if you really want to have recognize some large region here like cows, then you might need to have a very large receptive field to have the input here of all the neighborhood that comprises that cow here. So you either need a very large network, or you need very large filters so that the receptive field is large enough that you can capture a meaningful neighborhood of a pixel to be able to recognize that. D here in the middle is just the depth of the channel. So if you remember the lectures from Alessandro Giusti, I think it was he had some very good examples here, would be the depths that you get here. So for example, if you have a 3-channel input with a convolutional layers, you could have maybe 64 channel image for each pixel, which are intermediate results for the features. So exactly, it would be the depths here, and at the end you want to have the number of classes, but in between you usually have a larger amount here. Okay, so how do we get these larger receptive fields in the normal convolutional networks? We do it, as we have seen, actually by downsampling. So the images get smaller while they go through the network because you have those strides in the convolution, and you also have those max pool or average pool operation. So you would like to have something like that. So maybe you do some downsampling, and then you have a condensed image here where each pixel captures the feature from a larger neighborhood, and then you would like to go up again to the full resolution. Why? Because you like to have a prediction for the full image, so for every pixel that you had in the beginning, so we'd like to receive the same resolution that you have at the end. There was a question, is there a technique to label each pixel? You need to have the labels from the beginning to do the training. So you will have to you will need a data set with labeled pixels to do the validation, but also for the training. Okay, so we have seen this path is not so hard to do. The downsampling can be done by the pooling or by the strided convolution. But if you want to do it on the upsampling, on the other hand, how can we do that? How can we upsample the lower resolution image that we get here in the middle to the fuller resolution again? So let's look at that. So let's go back quickly how some of those operations work. So let's look at the pooling operation first. So for example, max pooling, a 2x2 max pooling would replace every 2x2 neighborhood with its maximal value. So you see you have an image of half the size than you have here, and of course you have lost all the information about those known maximal value here. Similar to average pooling, average here, you have the value here, and again half the size, and again you lost some information here, but here you have the average instead of the maximum. So for upsampling the pooling layers, we can do something that is called unpooling. Easiest method is just you use nearest neighbor. So in the middle, you will have your response at after resolution. For example, you would like to unpool it, upsample it to an image that is doubled in size. So you just make an image doubled in size and take the nearest neighbor. So you would expand this 6 here to the 2 by 2 neighborhood and fill the 2 by 2 neighborhood with 6, 4 here, with 5 here, with 2, and with 6 again here. Another possibility is to use so-called bed of nails. Nails is you just have one peak where your actual value is here. Excuse me. And so you put the 6 in here, or the 5 in here, the 2 and the 6, and you leave the other values here at 0. So of course the values at 0 are not so convenient then for the later step, but you could follow this unpooling by a normal convolutional layers that will distribute those 6 in the neighborhood, and then you have again some values at each point. Another possibility that has been found out is max unpooling. So if you go back to the last slide, you have seen I have no idea where to put the 6 here or the 5. So I just put it at one position, upper left corner here. It might be a bit better if I could actually put the 6 there where I took the maximum in the first place. So here the 6 comes from that pixel here, here the 5 comes from that pixel here. So I might want to put the value back at the correct position, and there it might be more useful than for the detection there. This is what's called max unpooling. So for this, in order to work, you need to remember the position of the maximum that you took for the max pooling. And then later in your pipeline, you will be at the corresponding step where you want to do the unpooling. You will have different values here because whatever the network calculated for those values, but now you will put the value at the same position where you took the maximum in the first place. So the 2 here will go here, and the 4 will go at this position because in the max pooling layer you took the 5 from this position here. Same as the other ones, the 6 here and the 2 here. So in order that to work, you will have to remember that, and you need kind of a reference to the layer where you took the max pooling from and the layer where you applied in the unpooling. Yes, so for that to work, it kind of needs to be symmetrical, or it could be symmetrical. You could have something unsymmetrical in between, but like for the corresponding step here, you will need to have an image which is the same size than the one that was produced by the pooling operation in order to apply it. So usually they are made then symmetrical. Okay, so with this, we have actually solved the problem of unpooling for the or for upsampling for the pooling operation. Yes, question was, are there any special layers in TensorFlow? I have to check. Unpooling, the normal unpooling is available in Keras. I'm not sure that this is available in Keras directly with using the max. So the upsampling is there, but with the max value, I'm not sure. But I say it's a possibility. Personally, I think it does not give that much of an advantage that you just put the pixel at the right position. Okay, so for the unpooling, we have done. We could do the upsampling. The other problem that we have is the convolutions. So we have strided convolution. These are the convolutions that would reduce our image size. If we don't have a strided convolution, if you have a convolution with stride equals to 1, we get an output for every pixel. So there is no downsampling. So we also do not need to do upsampling. But if we have a convolution with stride 2, what happens is first we will look that part of the image for a 3x3 filter. We apply the weights to calculate one value here, and this will give the value of that pixel. And then with a stride 2, we move from that center position to the new center position. Calculate again the result of applying the filter in that value, and this will give you the next pixel. And again now the size of the output image will be half the size of the input image. So we actually move 2 positions in the input for every position in the output. So what can we do instead? We do what is called so-called transposed convolution. It goes a bit by different names depending what paper you read. I will call it here a transposed convolution, and the idea is you upsample, so you replace your one image to the larger regions that you have from the filter. So one by one pixel here will get replaced by the filter values of your 3x3 pixels here. So this green here does not indicate that it's just the value of this pixel here, but this is the result of learning the filter values for this transposed convolution. So the advantage here is that you can actually learn how to do best this transposed convolution, how it works best. And then every position that you move here, you will move 2 pixels in the output so that you get a larger image. So what happens when they overlap? So if you go to the next pixel here, you will go 2 pixels in the output. You will replace again pixels here with the filter values, and where the filters overlap from the regions, you add. You'll probably have a filter that has less values here at the edge than it has on the middle here. And the same when you do then the pixels for that and that region, they will overlap here, and so this will add to those pixels out. So this would be a transposed convolution, strided 3x3 transposed convolution with stride 2 will make your image larger. Okay, so now we can actually go back to our fully convolutional networks. So now that we have solved the problem of upsampling with unpooling or strided transposed convolution, we can use network architectures that will first do a downsampling of the image, as we have seen in more conventional neural networks. You go to a lower resolution intermediate representation, and then use the upsampling layers to again get high resolution results. We will see later a bit, this is also a bit similar to a so-called encoder or decoder architecture, where you force the network to specify some lower dimensional feature characteristics in the middle before blowing them again up at full resolution. Questions so far? Okay, there is a different, or actually a similar but a little bit different approach. Another architecture that often comes up. It was used for biomedical segmentation first. It's from the University of Freiburg in Germany. And this is the so-called UNet architecture. So it is quite simple, quite similar, that you have different convolutional layers that will reduce your image, and then you do it very symmetrical. When you're at the lowest resolution here, you again go up to fuller resolution by upsampling. Additionally, instead of just using upconvolution, they try to retain some of the information of the early convolutional layers by direct connection between the layers in the early stages and the later stages of the same input by just copying those layers here and adding them at the input here, and then the network has some information about the values at this stage and could use them, for example, to maybe better distribute the features that it found here over the pixels here. There was a question about subpixel convolutions. I'm not quite aware of that, that this is much used. Usually for most segmentation, it's okay just to calculate a pixel level and not that you have to interpolate between the pixels here, but there might be applications. Okay, so an example of such an architecture is, for example, in this SegNet demo. This is actually a link that you can try out to get an instant segmentation. It's a segmentation of, here they do some outdoor photographies where they try to detect sky and road, buildings, etc. And you can load any image here, or you can select the image from a country, get a random image, and then it will get the result here. Thanks for the question about the supervision. I will look at that and give you more detailed answer then later. Okay. So I also want to show a quick example from our side, from a project that I've already described in last week's lecture. The idea was to have some classification approach to detect eczema on the image, and last week we have looked at the feature-based approach where we tried different features and then use a support vector machine classifier to do that. And we were of the we thought that this really would work good with convolutional neural networks. So at that time, it was about I think 2014, 2015, the convolutional networks just started to appear, and we just wanted to try them out for that. With some first methods, so we had some approach with the fully convolutional approach of the SegNet that we have seen before. There was also some masterwork on it, but unfortunately we didn't really get that good result by just using that architecture here. Why? So we thought we really have to segment the images using information on a very fine granular level, like eczema. There's can be detected maybe that your skin is a bit drier and it has some gaps and so, and this could be detected by some really filters with small values, and we thought we might lose a bit too much of the resolution then to detect those things. Also, the SegNet has really a large receptive fields of 200 by 200 pixels, which works fine if you want to detect like buildings or roads, but for eczema, we actually thought we didn't need those 200 by 200 pixels. So if you go to a doctor, he will take a magnifying glass and just look at your local neighborhood there, and so in pixels that might be 30 by 30 pixels, but not so large. So our first idea was then to go back to like the original idea of fully convolution networks, namely do everything in full resolution and not use any downsampling at all. So no strided convolution, no pooling, everything in full resolution. And then we will see that actually works out quite nicely, but it was a bit harder than to train the images in full resolutions, because you need also much more memory if you have in every step for the filters, you have the image at that resolution here. So one problem was that if you have images that are quite large, so here we at the end we had some 4 pixels images, and if you put that image in the network, then you could only process like one image. But you don't really want to process information of one image at a time, because then the image, the pixels in the image will be quite highly correlated. You would rather use some different parts of different images and mix them so that the network can learn the more general features of those images. And so in order to do that, we divided each image into some patches, and we wanted to do it as full resolution. So if you apply the convolutional layers, so for example at the end we had something like 10 or 12 layers, we will have a border in the image that was not able to be processed by the convolutional layers, and so we made the patches so that they have a slightly overlap, so that the processable areas where we get the results from would have no overlap. So in fact that every pixel of the image could then be used, and be used only once. So then we put those patches together, and as you know, you usually train a network in batches. So we have a batch of input patches and our neural network, and we also have the corresponding labeled patches, and the idea now was for the network to be trained that it finds the correct labels. So at the beginning we really tried a lot of different networks. I think it's always good to start with rather small networks, because then the learning goes faster, and then when you see you don't have enough capacity for the network, you can increase the network until you have better result, but possible overfitting, then you could go down again or use some regularization. We will actually look at some of these techniques then again next week here. So we tried larger and larger networks. These were a bit similar to the VGG architecture, like only with 3x3 resolutions, 3x3 convolution filters, and doubling the depth every 2 layers, and then followed by a detection stage that corresponded to the fully connected layers converted to convolutional neural layers. We also tried some completely different approaches, like idea to have some different branches in the network similar to inception, but just larger branches, which would force the network to like work at a higher resolution and a deeper resolution depending on where the pooling layers were. But actually this was a nice idea, I thought, but it didn't get really better results. At the end, our actually best performing network was similar to ResNet. So we used those ResNet architecture with the skip connections between every 2 layers, where the input here, the output here is added to the output from that layer, which allows to make the network deeper and has a better gradient flow, and also allows, if you have more layers that at the beginning do not do anything, they will be close to 0 and they will not disturb the training here. We also, just for comparison, if the ResNet actually works, it's some network which is the same but without the residual connections. So at the end, the variables are not that large in those networks. So we have about 30,000 variables there. And so at the end, the best network was actually the ResNet. And the non-ResNet was just a little bit harder to train, but not much worse. And some VGG-like network with that doubles the depths in every 2 steps. So we applied them then to our first data set that we had with this, you might remember from last week, where we didn't use the photo box yet with the green background. These were just images taken at the hospital by the photographer at the hospital, and then afterwards labeled by the doctors. And so unfortunately, but we were not really better than the support vector machine. So on average, actually, it was a bit lower the scores. So we concentrated on the F1 score because we had such a good data set. There were some results that were better, but it's wasn't really significantly better than the support vector machine. Here also I have to say that the master student actually that worked on the support vector machine worked almost a year on that data set, so he really had the best features for the support vector machine. We then repeated the experiment to the newer data set of the photo box with higher resolution and the green background. We used the same support vector machine features than for the other data set and also the same network. And here then we saw that the convolutional neural network was slightly but not much better than the support vector machine. So again, with a F1 score of about 40, a bit above 40% here. So this was done with a 5-fold cross validation, so that's why you get the standard deviations here and the min max of those box plots. We also looked a bit of what can you do with the parameters of the network and of the training. So, for example, we had two data sets, one with images only from July and August, and one with the training data set of 3 more months of images. And one question was, do the scores get better with more data? And also we varied the threshold. So the threshold determines when is it eczema. So is it when the prediction is 50%, we mark it as eczema, or when the prediction says 70%, we mark it as eczema. So what happens if you just change the threshold, then this is quite a clear observation. What you actually trade off is you trade the metrics of precision against recall. So you get a better precision because you get more of the true positives that were actually positive. You get less false positive, but at the same time your recall goes down, while the F1 score then remains similar to before. Went a little bit down. And with more data set and the same threshold here, we actually did not get a better result. So that was actually, I think that was a good result. What does it mean? It means we had enough data. So more data set does not show any additional features that were not yet present in the first data set. So if you just have enough data, then adding more data will not give you a better score in general. If you do not have enough data from the beginning, then of course more data which shows aspect of your data set that was not present before will give you a better result. So based on first result was similar than to the support vector machine case, that if you have a lot of eczema and you get a very high F1 score because you really predict a lot of it, you miss some of it. And if you don't have much eczema here, then the prediction here was not so good because it picked up all eczema here where there was none, then you get a rather low score. Okay, so from our experience, it works actually quite well. So you can do a fully convolutional network that preserves the image size without any down upsampling in that special case of local texture recognition, so for medical cases. Also, we tried with some pooling or no pooling layers and found that in that case also pooling layers did not improve the performance. It was better not to have the pooling layers. Also, it was better to have deeper networks but narrower, so not so many depths in the intermediate step, but a deeper network which has then a larger region to process. Also, we used some regularization and dropout that improved the results, didn't do a batch normalization, and we weighted a bit the data set to correct for the unbalanced net. It was really worth doing a bit their own architecture to learn what works best. At the end, the result was only slightly better than a support vector machine, but, and this is the main advantage of the convolutional neural networks, it was much easier to do. So we didn't need to do any feature engineering of what features might work best on that data set. You just end-to-end train the network. It might take 2 days until you have a result, but there is not much input that you have to give. So you have to give some of the hyperparameters. We look at that in the next lecture to start the training. But once you have a network that converges, you can easily optimize it. Okay, we will have a short break now, and then we will look at some example in Keras, how to do a fully convolutional network, and that will also be then continue in the exercise in the homework also that I will present then next. That will be a bit larger homework, similar to the first one that you have from Alessandro Giusti for the end, until the end of the lecture. Okay, but so let's have a short break and see you in about 10 minutes then with the Keras example. Okay, I hope you had a nice break. So let's look quickly at some examples for fully convolutional neural networks. This is also the first part actually for your exercise for today. The exercise will be rather smaller, but as I said, there will be homework that will continue a bit over the next weeks that you can also then work on today. You have already seen keras in the exercises that you did in the first part of the lecture, and we will again use keras here for our network. So here I added all the networks. I actually just updated my TensorFlow yesterday to use the GPU. So as you might already have seen, if you have convolutional neural networks, that really benefits from having a GPU. It should still be possible to train the networks without, but of course this speeds it up a bit. But I've seen it's a bit shaky. It does not always work so well on the on Windows for me. Now we could start with a real data set, but I found it quite useful to have some artificial images made to have just some basic tests for the network, that you see that your network actually trains and converges in those cases where you expect it to converge. And let's make those images for also called like smoke tests, so that you could run them through the network and you see that you have everything correct with the number of channels and the result and everything before trying it on a real data set. So what we will do is we have a function here that generates test images. So the test images have a mean value of two values that you can give here. The first value will correspond to class number 0 and the second value to class number 1. And they will not just have that value, but they will have added Gaussian noise to it. So if we just make such an image, we will get result, the image and the label. And for semantic segmentation, our label contains the label at every pixel. So we actually make a label image of the same size than our input image. And here an example. So this is a generated random noise images of one class. And then the network should be able to identify those two classes from each other by receiving that input. Of course, training in neural networks is done in batches, so we need a function that generates just some batch. And we also just use it here. Here I really made a normal image with values between 0 and 255, but as you have learned, it's best to normalize the input of neural networks. So here we normalize it between 0 and 1. Could also be able to normalize it using the minimum or maximum values. Okay, and here just be able then to generate a batch of images. So I have a batch of 100 image of that size, and it's a grayscale image then. So let's first try a simple full convolutional neural network. What do we need? We again need a sequential model here for keras. It's just a network which layers one layer after another. I usually like to specify the first layer separately with the input. So in keras you need to add the input shape to the network, and then we can add our convolutional layers. So I think you have seen that already. So number of filters here will determine that D or the depth that you get at the next step. Then kernel sizes 3 is we use a 3 by 3 filter. You could also use a tuple here with then if you want different sizes in width and height, which is usually not case. And here we use padding, same, so that we retain the image resolution. I actually prefer padding equals to valid, so we don't artificially add some values that are used for the convolution. Then still that will be one task, then exercise to change that. So at the end of what you normally would have your convolutional layers, you then have the part of the network that should do the actual classification. And as we have seen, we also need a convolutional layer for that. The convolutional layer should go to the number of classes. In our case, we only have 2 classes. We use sigmoid, so we only have 1 channel here. Normally, you would have the number of classes here, and then you would have softmax as the activation if you have more than 2 classes. And one by one filter, and I added the activation layer here specially. So that would be our function to do the model. And let's see, because it's only convolutional, it doesn't really have much parameters, but let's see if that works. So loss function is after sigmoid needs to be binary cross entropy, and we, for example, look at the accuracy, and let's see now if we can calculate something with that. Okay, that was fast, but probably not so good. Okay, loss continues. Accuracy for such easy data is not yet good enough, so probably I didn't train enough, so maybe I should have some larger batch size here or some more epochs, so we can just continue training and see if it continues. Which gets a little bit better, but it's a bit a strange curve that it produces here. Okay, and as the loss still goes down, we probably need some more training here. Okay, so what we have done here with the batch is that we put 1 batch of images in the memory, and that is all of our data set. Then we go through that in time. But normally, if you have a really large data set of images, you will not be able to fit all your data set in memory. So you need some different techniques for that. And there's 2 possibilities. One is TensorFlow datasets. We will look at that next time quickly. And the other is with generators. And the generator is just a function that will generate the image when it actually needs it. And here, as we do our images, as we construct our images, it's very easy to do. The generator, if you have a generator and your images are on file, then your generator could use, will read the images from the file system and then produce them for the system. So with a generator, you have some loop that will run forever. You generate a new image, and then to provide that image to the learning algorithms, you use the keyword yield, and then you give back a new image batch and the label batch here. If you use that in Keras, you just you can do the same as before. So we make a new model for our neural network. We combine it as before, and then except that we instead of using the model fit function, we use the function model fit generator, and then we have to specify the generator. Because it uses a generator, it does not actually know what the epoch is. So how much time, how many steps are needed for a whole epoch. So this is something that you will have to provide for the model fit generator function. Okay, and now we can train again. Train a little bit longer here. Now with 10 epochs and 100 steps in. And we see that with the longer training, it already gets some better results. So we have accuracy of 1, which is actually what we should get since this is a demo data set that we artificially created, which is quite easy then to recognize. Okay, so using those full convolutional neural networks in Keras is quite easy, I would say. So the only thing that you need to remember is that you will have to change here the last layers to also be convolutional layers instead of the connected layers. And here we just use just convolutional layers. So for the homework, then you should try to build a network that can be trained on this describable texture data set. And the idea is to have one network which has just convolutional layers, which is easier to do, and then one network which at least has some downsampling and upsampling in the network. Okay, now I actually would like to quickly look at the exercise from last week, where you supposed to do the texture recognition. So let's quickly go through that. And if you have any questions then to that, we can get that in Discord. So the idea was to use texture recognition, and with those local binary patterns and histograms. So the idea was to use just 2 images and actually use then the descriptors from various parts of the images to do the texture recognition. So this was then in grayscale images, and then the idea was to use binary patterns. So you have to find out how to call these local binary patterns with different arguments like the radius or the number of patterns that you use. This will give you back just an image with the binary pattern as an integer number for every pixel here. If I just use 8 channels here, I will actually end up with an image with 256 different values. So you could just look at those binary patterns and then the image that are generated by them. So for the texture segmentation, it does not work that well to use just the binary patterns. The idea is we look at the sub window to check the texture in there, and then take the histogram of the different values of the binary patterns in that window and use that as a texture segmentation. So for this sliding window approach, you could of course just program out a double loop, which you would do in most other programming languages. In Python, you have these utility functions that gives you a view of the image as blocks or as windows, which could be used instead. So then you automatically get those sub windows. So if you use a view as blocks, and if you then actually plot all the blocks, then you will just get a small window for each block, and all of them together make up our original image here. And you could use the same as window. The advantage of that is that in blocks they cannot overlap, but in windows they can overlap, and then of course you get a bit more data for that. So here I made a window shape of the same size, but a step size of 4040. So I get double the amount of blocks, and they always overlap half a block. Okay, and now to do the texture recognition, the idea was to use the histograms in 2 of the sub windows. So I just looked at different windows so some arbitrary, the first and the second window on one of the images, and then the same on the other images. And what do we actually want? We want to find out if the histograms look similar from the same image as compared to from a different image. And so when you look at those images here, we see those two are the histograms from two patches of the same image, and those two are from two patches of the other image. And I think it could be said that those two look much more similar than the ones from the different image here, and the same here. So by looking at it, it seems very likely that we can use that feature for texture segmentation, and to actually compute it, we need to compare those histograms, and there are different values for that. So directly in the Science Python library, there is chi-square, and in OpenCV there are some more histogram comparison operators like Bhattacharya distance, which is also often used in image processing. We will just use the chi-square, which is a simple way to calculate, and we can just calculate the chi-square difference between all of our different histograms that we calculate. It fails if some values are 0 here, which happens. So we can add 1 to all the values. It will not change the shape of the histogram much. So first of all, if we compare the histogram to itself, we get a distance of 0. So that is good. If we have two values from the same image but from different patches, we get values in the order of here 700 or 170 here for the other image. If we compare histograms between two different images, we get much larger differences here than we get from images from the from patches from the same image. So it seems that we could use this histogram comparison to actually classify the image. Okay, we didn't continue here with the exercise to do the actual classification, but then you are supposed to look at these other features and supervised learning to do that. So the idea is to look at to calculate some features and then actually do supervised learning for. So for the features, we again divide the image into blocks, and now we want to calculate some features for each block, and those then should be used for the classification. So for example, we could just use statistical features, so we can just calculate the mean and the standard deviation of a block feature. Next, we wanted to calculate the gray level co-occurrence matrix. If you calculate it for 256 values, it will give a lot of numbers, and it might be a little bit noisy on the pixel level. So it's better to use it on less data or on less number of levels. So we only want to use it on 16 levels and then just divide it by 16. Sorry, this wasn't clear with the blocks flat here. I converted my blocks to a list of blocks so that I can use a single loop to run through all the blocks in the image here. Okay, I can just calculate one of those features here by just calling this gray co-occurrence matrix and telling it what do I want. There are different methods in which angles or which distances I should calculate this co-occurrence matrix. It's possible to use more than one. So if I use two different distances and two different angles, then I will get 4 occurrences matrix for every combination here. And as was pointed out in the lecture, we usually do not use the occurrence matrices directly, but we can calculate some features from the matrix, and those then should be used for the comparison. So I did that to calculate, and then we get those features. So we get 4 of those features because we have 4 matrices for every combination here. So contrast features, dissimilarity features, energy features, and more. And then what we do as a feature descriptor, we can just take the mean, the standard deviation, all the features from the matrix, and just calculate them all together into one feature vector, which gives us a vector of 26 features that describe this local neighborhood. And now we want to classify that using those features here. So we can use this flat representation of the blocks. I can just use list comprehension here to calculate all the features and get my data set as a stack of all the features here. So this I will do for both images here, then have my data and label data set, which 1581 samples in the dataset and the feature vector of 26 we saw before, and now I can just use that dataset for supervised learning. We should normalize it first. I want to shuffle the dataset so I'm more mixed up. Not all classes are behind each other, and then the idea was to use two different classifiers for that. So I could use a decision tree or a linear support vector machine to train the data. And I did here both with the decision tree or the support vector machine. In both cases, the results are very good. Of course, we should evaluate on the validation dataset, but for example, they were perfect with the confusion matrix. And why were they perfect? Well, we could look at some of the features to see. So here, for example, I plotted a scatter plot of two of those features, like the first feature and the third feature from the different classes. And you can see that they are perfectly linearly separable. And so they will get a result here from CPI. Okay, any questions for the exercise from last week? Okay. Then, so the exercise today will be rather smaller, that you work a little bit more with those example data set to get your first network up and running. So you should convert your example to 5 classes so that you see how you can train full convolution neural network for different classes. And then the homework, which is also available then in a detailed description on Moodle, is then homework until the end of the lecture, where you should use a full convolutional neural network on this describable texture dataset. Actually, we don't use the full dataset. We just use some region in the center of the images in the dataset, so that all the images have the same size, which makes it easier to use, and some of the image do not contain much of the textures near the border. So it will be a simpler data set. There is a routine details loader that will extract at the middle of the image for each images, and then also distribute the images into train, validation, and test data set. So your task will then be to use 2 fully convolutional networks to train and test the classification. It should be at least one network with only convolutional layers, so you can use what we have looked at today, and then it should be one network with down and up sampling, so that you can apply the techniques that we looked at in the lecture. The 3 data sets that you have, you obviously use the training data set for training. Then the idea is to use the validation data set for hyperparameter tuning. what does it mean? So maybe you want to add layers or you want to add channels to your fully convolutional neural networks, and then you will retrain on the training set. You will test on the validation set to see if you get better results then. And the test set should then just be used when you have your optimal networks, both at the very end, and ideally you would just run it once then to evaluate your scores for the test. Okay, any questions? So I'm not sure if Alessandro Joseph pointed out, there is the Colab Google environment where they have GPUs, and usually it's not available that you train for for a couple of days, but you can let it run for 1 or 2 hours, and that should be sufficient to train the dataset there. And also the Python script should be able to download the dataset then at that location. I think otherwise it's probably also possible in a CPU, but it will just take a little bit longer. But then it's also okay if you don't train that long, that as long as you get the experience of how the dataset, how the fully convolutional neural networks do their tasks and actually start to converge. Any more questions? Okay, then that would be all for the lecture today. So rest of the time is for the exercise, and please maybe also start looking at the homework so that you have any questions that we can address them as early as possible and resolve them. We will start a new topic next week, but I also go quickly over some tips then how to set up the training for these fully convolutional neural networks in Keras, which hyperparameters to quickly as a repetition and efficiently then work on that. Okay, otherwise that's all from me this week. So have a nice day, good week, and good then.